Hello everyone, my name is Karin Wolff and I'm a research fellow from the Cape Peninsula University of Technology in South Africa. Now, last year I presented a paper on engineering problem-solving case studies from industry and the important role that the different engineering disciplines play in shaping ways of thinking. Now today I'm going to be reporting on taking this research back to actual engineering educators. Now the original question, how do technicians work with physics, mathematics, and logic-based disciplines when solving an industrial problem, was sparked by observations of and reports on the disjuncture between science, the engineering sciences and mathematics, and the realities of complex 21st century practices evident in actual industrial sites. Now, with a move towards more project-based or problem-based learning in engineering education, my concern was the perception that the traditional discipline-based curriculum was outdated. So I literally wanted to see how these disciplines manifested in the world of practice. Now, using a number of analytical research design tools, I took into consideration the environments in which different problem solvers faced and solved engineering problems in relation to actual artifacts, in other words, physical systems. Now, a useful research design tool was Herbert Simon's distinction between the inner environment, dictated by particular phenomena and sciences, and the outer environment, consisting of context, stakeholders, and processes. Now, each case study constituted a holistic knowledge practice environment. Now, very briefly, the original studies looked at different engineering industries in the Western Cape region in South Africa. There were 41 case studies to date, focusing primarily on technicians and technologists who completed a problem-solving questionnaire and were then interviewed at the workplace in relation to the problem they described. In other words, they physically demonstrated and talked about what the problem was, how they'd approached it, and how they analyzed the causes and then solved the problem. And these interviews were all audio or video recorded and then transcribed. There are a number of papers on this already if you're interested in the actual more detail on the methodology. The key focus for today is the analytical instrument used to describe and interpret the problem-solving processes and how this tool and the case studies have benefited engineering academics. Now, the primary instrument is taken from one of several dimensions of legitimation code theory. The epistemic plane is what the tool's name is. Now, it's a Cartesian representation of the relationship between the what and how of any particular knowledge practice. Now, the vertical axis refers to the boundedness of a phenomenon, where strong means a phenomenon is recognized or accepted by the field as having a particular nature, and weak means something may be ambiguous or contested or far more open to interpretation. Now, the horizontal axis represents how fixed or open-ended an approach might be to the actual what that we're talking about. So we find the top right quadrant being about practices where all agree on a principle and its associated procedures, such as much of our core natural science curriculum. Now, where how matters more than what it is being applied to, we talk of working with doctrinal insight, like the scientific method or mathematics, where the what has multiple possible approaches, such as deciding on a control system. We talk of requiring situational insight. The situation will dictate how I set up my system, what it needs to do, what we can afford, but we all understand the phenomenon we're dealing with. Now, the bottom left quadrant sees either no insight or the practice is governed by a different set of relations, social relations, where other things count, where it's no longer about a phenomenon and how you approach it, but it's more about the context and the social context. Now, using this instrument, the case study transcriptions were analyzed for the process each practitioner undertook and their references to specific disciplines, physics or chemistry, mathematics, logic-based disciplines or technologies, for example. And these gave me a problem-solving map of each case study. Now, what we find as an overview in terms of the findings is that when most of these practitioners spoke about physics, this always occurred in the top half of the plane, in the purist or situational quadrants. For example, regulating voltage using Ohm's law or investigating the cause of blown capacitors. Now, mathematics references occurred across all insight quadrants. For example, power calculations in the purist quadrant, production efficiency spreadsheets in the doctrinal quadrant, programming algorithms in the situational quadrant, or even quantified operator errors in the Noah quadrant. Now, the situation and doctrinal diagonal sees most of the references to logic-based disciplines. For example, you design a custom-made system and it depends on the situation. It's in relation to feasibility, the financial and resource constraints, for example. But implementing the system depends on the doctrinal implementation of specific platforms and programming languages and systems. Now, I translated the map, for simplicity's sake, into what I'm now calling the 5P model, using terms like principles, procedures, possibilities, and people. Now, the findings regarding the disciplinary references being located in specific quadrants is really important. Each quadrant represents a code, a way of thinking, and the successful problem solver recognizes the need to think in certain ways at different stages and then shift his or her thinking across the problem solving process. And this is called code shifting, and it's an iterative process which can be explicitly taught. So what does this mean for education? So a key deliverable for my postdoctoral work is taking these research findings and the kinds of theories that underpin them back to engineering academics. Now, as part of an international collaborative project on enhancing engineering educator capacity, I'm working across two very different institutions. At a University of Technology, where I work with an entire department, the Industrial Engineering Department, and a research-intensive university, where I work across the whole faculty. Now, over the past year, I've conducted several individual and group workshops or sessions, primarily looking at the curriculum, teaching, learning, and assessment. And I'm going to show you 3 examples of how that epistemic plane and the industry problem-solving case studies helped these educators to rethink what they're doing. Now, the first case is that of my colleague Lydia Orette, who's also presenting at this conference. She observed the difficulty students experience in her process control subject when students move from the theoretical application of mathematics to solve maths and energy balances into the software space. In other words, their problem lies in shifting to the left-hand side of the plane. Now, at the traditional research-intensive universities, we find much of the curriculum on the right-hand side, the principles and procedures. And then the sudden shift to design or capstone projects located on the left-hand side. Now, by using a plant design assignment as an anchor across the entire course, she enabled students to iteratively work on subsections of their design, drawing on the purist concepts during specific lectures, and then the mathematical, more procedural focus of the tutorials, and then moving to the top left to practice in the software space, different kinds of software, different stages or moments, which also takes them back down into the doctrinal procedures behind programming, for example. Now, the intention was to improve students' ability to code shift diametrically in an ongoing fashion. Now, similarly, in an electrical engineering course, the educator teaches programming and wanted to encourage more consistent practice for the students. Now, the use of a platform such as Code Runner, in our case, is ideal because it enables code shifting between all 4 quadrants. With simpler kinds of questions, the students learn the doctrinal conventions around naming, syntax, and commenting, for example. Now, the iterative practice itself enables grasp of the fundamental purist, in other words, coding principles, such as consistency and simplicity, and bearing the end user in mind, for example. Now, students can engage with this platform, Code Runner in our case, in their own time and space. It also offers multiple kinds of programming that the students can work on. So in a sense, the platform itself offers a form of learning that can accommodate different student needs. Knower insight, in other words. Now, the third and final case study for today is also from a University of Technology, where the entire department is engaged in redesigning the curriculum. Now, one of the very first professional development tasks I facilitated was to use the epistemic plane to interrogate their understanding of the different qualification outcomes. The department were divided into 4 groups and asked to discuss what they thought the dominant insight or code or way of thinking was that underpinned each particular outcome. Now, what is really interesting here is that each group mainly agreed that number 1, in other words, the principles, engineering principles, was a combination of all the insights. And that number 2, the science, mathematics knowledge, was purist and doctrinal. However, they all had different interpretations of the remaining outcomes. For example, just the use of tools and techniques, number 5, was interpreted as either dependent on the situation or mainly procedural in relation to principles, or procedural in relation to people. Now, their experience of this task and the discussion that followed was that they understood how their students might feel when a new concept or term is introduced, and where the lecturer assumes that everyone will have the same understanding of that concept or term. In other words, they experienced this physically themselves, being that they all came to this with different interpretations. Now, the learning moment for the team was the necessity of A, making explicit what you actually mean and what is meant in the curriculum text, and B, shifting to different insights or different ways of thinking when dealing with any particular phenomenon. Now, what I've attempted to do today is demonstrate the usefulness of a theoretically and methodologically informed approach to enhancing engineering educators' understanding of the complexity of and relationship between the engineering profession and education. The epistemic plane enabled the translation of industrial problem-solving processes back into the classroom. Now, using the plane, one can see that it enabled staff to understand and engage with why, how, where, when, what if, and who in their teaching and learning contexts. They were able to interrogate and consolidate the principles of the profession and education. It helped them to see the kind of thinking required for different kinds of procedures. Using tools from other disciplines gave them insight into a form of multidisciplinary systems thinking. And at a personal level, many of the academics became more aware of their students, the stakeholders in the institution and industry. The tool enabled them to share divergent perspectives and to come to a common understanding of their role in the engineering education space. Thank you very much.